Very interesting, Stefan. So qubits can really fly.
Uh, yes, they can fly. They can move with the speed of light.
Great.
And this is exactly what we are doing, what we are building here. And also, Lars, our managing director, Germany, is here. And some of you might know we are building for the DLR, for the Quantum Computing Initiative, a photonic quantum computer. And the big difference between photonics and all the other challenging technologies like ion-based quantum computers and superconducting quantum computers is really that our qubits move. They fly around in our integrated photonic circuits.
Tell us something more about it, please.
Yeah, I will probably do. I will probably do. Are you happy with the sound? Wonderful. Okay. Who has heard of measurement-based quantum computing before? And other question, who's just only waiting for the bus to get out of here? Oh, that's, okay, you're in a superposition state, okay, great. Cool, so then I can just skip a few slides. Or maybe let's start with our mission, Quix Quantum. We would love to build a European quantum computer. This is the boundary condition, and European means in this case we have a fully European value chain. This is because we are based on silicon nitride photonics. We use foundries all across Europe, and Europe is quite strong in integrated photonics. We are a Dutch company located in Enschede. That's quite near Münster, just on the other side of the Dutch-German border. And there's a big clean room, a big foundry for silicon nitride photonics, and therefore our company came to quantum, because silicon nitride has somewhere, maybe half a decade ago, passed the threshold for quantum computing in being that kind of lossless. Just to keep in mind, why are we doing all this effort? We're a company with 30 employees. We're rapidly growing. So why are we building a quantum computer? And I like the statement of Feynman. There are a lot of problems on this planet which are quantum-like, or at least which math is quantum-like. And if you want to solve quantum-like structures, quantum-like problems, it's a good idea to take a quantum computer for this, to have an advantage in speed up. It's not that a quantum computer in principle can do things that a classical computer cannot do. I think the point is that it's really faster in some applications, dramatically faster. So you all know the applications that we want to target. Let's directly jump into the topics, why I believe, my background is photonics, but why I believe that photonics is the right solution to building a large-scale quantum computer. First of all, photonics is modular. We built a photonic quantum computer out of tiny little chips, microchips, out of silicon nitride. They work at room temperature. And if you want to enlarge, in principle, a universal photonic quantum computer, all you have to do is just take a few nearest neighbors of channels and interconnect them to the next neighboring chip. So it's highly scalable, it's modular. We have a quite mature basis, as mentioned before. Our company was started because we have great integrated photonics, and it was our co-founder Jelmer Rennemar who found out in 2019 or 18 that this photonics is suitable for doing quantum experiments on chip. So instead of doing all the interference on bulk optics, on a lot of optical tables adjusting 2000 beam splitters, what we do is we bring this all on chip level and integrate it, and therefore it's affordable. I think it's a wafer-based process. The development is quite expensive, to be honest, because one wafer run is 150K plus. That's quite an expensive hobby. But on the other hand, it scales. If we want to manufacture 10,000 chips or even 50,000 chips, we don't really care in the end. It's the same process, it's wafer scale. It's affordable in that way, and it's also forgiving. We can quite lose a lot of photons. So I have to look at Ish, who is the expert in error correction, and at his face, I think 20 to 30% of photon loss, yes, thumbs up, is something that we can accept. If we compare now the physical properties of all the different, we call it the different churches. You can believe in ions, you can believe in superconducting qubits, and to be fair and to be honest, I believe that all these technologies will coexist during the next 10 years. So there's no champion currently, all have their advantages and disadvantages, and of course, since my background is photonics, I can tell you best about the advantages of photonic quantum computing. Gate fidelity is something where I really expect all the technologies to be on an equal level in a few years. So there will be workarounds. We can fight about, okay, what's your fidelity for a 2-bit gate? What's your fidelity for a 3-qubit gate? But in the end, fidelity isn't a big showstopper. Qubit lifetime, their photons are a bit special because there is no physical qubit lifetime. You can find photons flying through the universe from the Big Bang. They don't really lose their information, right? So it's more about not losing too many photons. This is a technical challenge, an engineering challenge. We need to make our photonic integrated circuits in a way that we don't lose too many photons. We are working at room temperature. This is, for me, the biggest advantage. Only the detectors need to be cooled, 2 to 4 Kelvin, which is quite a warm cryogenic temperature. So it's the Hawaii summer holiday for cryogenics, so to say. It's not 20 millikelvin, right? It's a 19-inch rack of cooling effort that you need. We have all-to-all connectivity if we want to, and the scalability, this is the point I really want to make today. The scalability is horizontal. So if we take one of our chips, this is a 20 by 20, 400 interferometers on top. Usually if you buy one, you get it boxed in a nice 19-inch rack, plug and play with a USB port. You need to attach your sources and your detectors, and then you can just build your own special purpose quantum computer. This is, however, the pure chip. And if we want to scale and we really need 100 logical qubits, that means a factor of 100 to 1,000, maybe a bit more physical qubits in the end. So a ton of chips, a ton of qubits, then we just have to interconnect, in principle, those chips. And this is why I highly believe in this wafer-scaled manufacturing process of integrated photonics. What have we achieved so far? So with this technology, the company is selling now these photonic processes to experts. So you need expert knowledge to operate a processor. You need to buy your own detectors. You need to be an expert in quantum optics to understand what's going on there. And from that point, we decided one day to become a full-stack hardware quantum computing company, because there are not too many people out there who have interest in building their own photonic quantum computer. That market is quite limited. And also because of the fact that are not really manufacturers for the beam sources that we are really looking for in that field. So we also applied for the DLR Quantum Computing Initiative, and we won a contract over 14 million, and we are quite happy that I can announce today that we already delivered the first hardware. And this was, that was on time and also fulfilled all the specifications. That happened 2 or 3 weeks ago. So once again, congrats to our team in Ulm who made that possible. And this is really the easiest setup for a photonic quantum computer that you can make. This is photonic quantum computing for beginners. We have a processor, we have a power supply, control unit, photon sources. In this case, it's a down conversion source that our employees in Enschede just assembled in 2 weeks. We have delay lines. This is a bit more tricky. And in the end, we have detectors. And this is the fundamental basic building blocks that you need for making a special purpose quantum computer. This one is not universal. And from here, we will take it in the next 3 years to make a universal and error-correctable machine out of that. And then we have another interesting collaboration going on that we announced last year. And this is really the partnership more to the software and service side. So as I mentioned, we are a quantum computing hardware company. So our stack ends more or less with a library where we can enable our customers to make quantum operations on our system. And then we have partners like QMware who want to grant their customers access via the cloud, and also a little bit more software and application knowledge so that you can start to play around. So our system, our first system, which we have in Enschede, is more or less a clone of this one, will be cloud accessible beginning in January next year. So it's already cloud accessible, but in the test phase. Yeah, and this is coming back to the hardware, really. This is the processor. This is the core of a photonic quantum computer. No cryogenics, scalable, producible as a mass product in the end. And it's completely based on R&D activities in Europe, and we are quite proud on this. This enables us to make very fast iterations. And how much time do I have left? 2 minutes, okay. Then let's make a quick introduction about one thing that's really special and that you have to realize if we talk about photonic quantum computing. So there are a lot of advantages of having photons as qubits. However, there are also a few challenges. Like a qubit is not a two-level system. How can we make a qubit out of this? And they are moving with the speed of light. You all know gate-based quantum computing. You all have tried Qiskit, I guess. You have input qubits, you apply the gates, you perform measurements, in principle. Now, measurement-based quantum computing is a bit different, has a few more degrees of freedom. So we turn around this a little bit. What we do is we first create a big cluster state, and this is also the challenging part. We take the photons and we entangle them. And after having created this big cloud of entangled photons, then we perform the measurements. And depending on the outcome of the measurements, we change our measurement basis. For us, that just means we change the value of a phase shift a tiny little bit. And so this is creating this cluster state, and this gives you a lot of degrees of freedom. And this is the last slide, I promise. If you understand this, you have understood really the difference between measurement-based and gate-based quantum computing. So this is quite essential, the setup. We have sources, we have a big interferometer. The only thing that photons can do is interfere, or you change the phase. You wouldn't like to change the amplitude of a single photon. That doesn't really work out. Then it's just gone or there. It makes no sense. And you have detectors in the end. And you have some delay lines underneath. And now the tricky point is we create our photons, we send them through this big interferometer of entanglement, and then we can send a few back. And this is a nice multiplexing step, time multiplexing. So what we can do is we can take one of the output photons, send it to delay line, and entangle it with the next clock cycle of photons coming. And therefore we can create a cluster state also in time. So we don't need, if a calculation requires 1,000 qubits, we don't need 1,000 input ports. So we can really think about, how many qubits we need at a certain time. And this is for me, this is the big advantage of these flying qubits. I don't need all of my qubits that I, in principle, require for calculation at the same time. And this was the point I just wanted to make. I'm quite happy that Ish was nodding all the time, so it wasn't too bad. And hopefully correct.
Thank you very much.
And I think that's a great point here to stop.
Thank you very much. Thank you very much, Stefan. We have maybe a little time for one question. Thank you.
Right. In terms of application, I have to stick it in my... In terms of application, how different is the usage of this computer compared to the gate-based? Will you be attacking the same class of problems, or you have something extra, or how does that look?
Geht es? Es geht auch. It's exactly the same. So there are also some papers out there. Meanwhile, there's one from QMware that shows that you can, in principle, convert everything that works on a gate-based logic into measurement-based logic. So it's more or less exactly the same way of thinking, but implemented in a different physical approach. So it's no difference.
All right, thank you very much, Stefan.